Okay. So an important announcement is that, so today again we have a colloquium at 4 p.m. The speaker is Laura Matusevich from Texas A&M. And really I couldn't have planned this better. This is the perfect talk for you to go to if you're taking this class. Laura is actually a former student of Bernd Sturmfeld's, and her research is on what we're doing right now, basically. And she's going to be talking about what we're doing right now. She's going to be talking about binomial ideals and how you do primary decompositions of them. And I actually want to take a few minutes at the end of class to remind you a little bit about primary decompositions so that you'll be, or tell you about primary decompositions. Have I told you about primary decompositions in this class? So I should tell you then. I'll tell you I'll tell you about primary decompositions, and then in the talk she will tell you how to do that for a binomial ideal. And it's going to be the same story where basically, because binomial ideals have nice pictures that we can draw, then we can do this very general procedure in a very concrete way. So you should really, really go to this class so you can see what the current state of the art is on these things. Okay. So we were talking about semigroup rings and lattice ideals. So it goes like this. You have an abelian group A. You have a semigroup which is generated by some elements of your abelian group, which I called A1 up to AN. Okay. And I want to leave this picture up for the whole class, I think, so that we remember how this goes. So my favorite lattice is, I don't know, a nice abelian group is Z2, okay? And so here Z2, you should be considering this as an infinite square grid. It's infinite in all directions, and Z2 are the vertices of the square grid. Right? Then I take three elements of my square grid, in this case 3, 0, 1, 1, and 0, 2. And so of course that means that this I'm considering as the origin. Okay. And then I'm taking all the natural combinations of these guys. Okay, so I add them in every possible way, and we did this very carefully last time, and we got all these points, Q. Right? So we saw that this was kind of a fun game to play, and what turns out in the end is that once you're at this point, then everything northeast of that is in my semigroup, but there are these gaps around here. Okay? And this is generally what semigroups look like. There's kind of gaps at the beginning, but then if you look far away, they look pretty regular. Okay? We'll make that a little bit more precise. So we have that. Then we defined a lattice. And I defined this in a certain way, but I want to maybe say it a little bit differently today. But in a way that, I mean, it's equivalent, of course. What I want to do is consider, let's say, points, what's a good letter? Let's say L1 up to Ln, and these should be integers such that L1 A1 plus dot 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 plus Ln AN is equal to 0. Okay. So if you look at the definition that I gave last time and the definition that I'm giving this time, you're going to see that they're equivalent. But I actually think that this definition you will come to like better. Okay? Because what I'm saying here is that basically you want to consider all the integer combinations of the AIs that are equal to 0, and you're going to tell me what they are, and that's L. Okay? So these are the You can actually kind of think of these as syzygies, right? I mean, this is like a syzygy between A1 up to AN. So these are the integer relations between the AIs. Okay? So for example, we did this a little bit differently last time. So if you remember, the way that I explained this last time is that you had a homomorphism from Z3 into A, right? And we had this homomorphism up here. So I basically had Z3 living up here. And I guess I drew it like this. And these were my basis vectors. And then I said, so this is Z3. Then I define a homomorphism here that sends each generator, E1, E2, and E3, to A1, A2, and A3. And I define L to be the kernel of that map. Okay? But if you think about what that means exactly what I'm saying. Okay? For example, 2 minus 6, 3 is in the kernel of that map. And the reason is that 2 times 3, 0, plus minus 6 times 1, 1, plus 3 times 0, 2 is equal to 0. So in other words, what I'm saying is that 2 minus 6, 3 is an integer relation between these three guys. Okay? So this is, you can think of as relation between A1, A2, and A3. Okay? And you see, when you think about it from this point of view, it's a little bit clearer that this should look like this because, you know, we have three vectors, right? We're looking for relations between them. And we have three vectors that every two are independent. So actually, I only have a unique relation, which basically says how to write one in terms of the other two. Okay? 6 times the middle one is 2 times this one plus 3 times this one. And every other relation is a multiple of that. So that's why the lattice is just the multiples of that basic relation. Okay? And then the lattice ideal is basically turning this into polynomials by using them as exponents. Okay, so the definition looks like this. So the lattice ideal I sub L, we said, was the ideal of things of the form x to the u minus x to the v, where u and v are in n to the n, and u minus v is in the lattice. Okay? But the way that we thought about this very concretely here is that we said every generator of I sub L is a binomial, right? And the binomials that you get to put here are things like 2, 0, 3 and 0, 6, 0. The condition that they should satisfy is that when you subtract them, you fall in your lattice. Okay? And in this case, this single guy generates everything. Okay? So this is kind of the general setup. And I guess I also, so there was another definition. Of the semigroup ring, and this was just the ring generated by things like T to the A, where A is in Q. Okay. So in this case, remember we said that this thing was already generated by these three guys, right? So T to the 3, 0, T to the 1, 1, and T to the 0, 2. So these are the generators of our ring, and then you can just go crazy and add these guys and multiply these guys and multiply by scalars. Okay? And actually, I should have defined these two things in the opposite order because this is the ring, and this is the ideal of the ring. Right? In order to define an ideal, you have to say what ring it lives in. And this is an ideal inside this ring. So that was the general setup. Did you guys have any questions about it before we start proving theorems? And I remind you, I asked you to do an example of the semigroup generated by, I guess I said, 2, 0, 1, 1, and 0, 2. And if you haven't done that, I still encourage you to do that. So exercise, for your own sake, do all of this for this guy. 2, 0, 1, 1, 0, 2. Okay. So just to give this thing some names, so this is the abelian group. This thing is the semigroup. This thing is the lattice that we get from the semigroup. This thing is the semigroup ring. And this thing is the lattice ideal. Ideal. And it lives in the semigroup ring. Okay. So this is the general setup that we're working with. So I want to prove a theorem, an important theorem that says the following. The semigroup ring, which I define like this, is isomorphic to the following thing. It's basically R mod. Wait, sorry. Okay, let me back up and say something a little bit differently. I got confused for a second. This lattice ideal does not live in the semigroup ring, right? Because here the variables are x1 up to xn, and here the variables are the t's, right? And here the exponents are natural numbers, and here the exponents are elements of the semigroup. So actually, each one of these things is, and you can see it there, right? The semigroup ring is in variables x, y, and z. Sorry, the lattice ideal is in variables x, y, and z. So this thing naturally lives inside the ring F, like this. Okay? And this is what I call R. Okay? So that's more like it. And now my statement makes sense, because basically, if I want to be able to take the quotient of a ring by an ideal, then that ideal better be an ideal of that ring. Okay? So what does this say here? What this says is that, I mean, you see this is a very nice statement because it says that this semigroup ring, which is a little bit weird, right? We're defining it by these generators, and these generators have these exponents in a semigroup. But actually, what we have here is a theorem that tells us that this thing is isomorphic to the polynomial ring in 3 variables modded out by the lattice ideal. Okay? And that brings it back down to earth. That's something that we're used to. It's just a quotient in a polynomial ring. Question? T1 and T2. So basically, T is a vector of variables Ti's, and you have as many as you need to make sense of this. So for example, when I write this, really what I mean is T1 to the 1, T2 to the 1. Actually, I'm glad you asked that question because I think this is going to help make the proof a little bit clearer. Okay? Because what we're going to do is that basically, here's Q, right? And we're making a ring out of it. And the way we do it is that we take each one of these things and we say T to that thing. Okay? So let's take this guy. This is 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. Okay? So this thing gives me an element T1 to the 6, T2 to the 5 in semigroup ring. Okay? So the semigroup ring you can kind of think of as this, except that there's a whole bunch of T's. Okay? For each point, you have a T to that point. Okay? So that's the left-hand side of my theorem. The right-hand side of my theorem actually lives more naturally up here. Okay? Because R is the ring of polynomials in n variables. Okay? And this is z to the n. Okay? So I can also think that Z3 is in itself a lattice, right? So I only drew the generators, but if you really want to think about this correctly, C3 is just all the integer points in R3. Right? I don't know, should I try to draw it? Probably not. Let's try to draw it, a little bit of it. So it looks kind of like this. So there's a little cube here, and it's just a whole bunch of cubes like that. Yeah. So this is what Z3 is. Okay. And now I'm taking this thing and I'm making it into a polynomial ring in the variables x. That's what I did. So for example, I have a point here, okay, and this is x, y, and z. Then this point, well, it depends how I drew this. Let's see. It's x is 0, y is 1, z is 1. So this is the point 0, comma 1, comma 1. And I take that point to make a monomial, which says x1 to the 0, x2 to the 1, x3 to the 1. And this lives in my polynomial ring R. Okay. And this point 6, comma 5 gives me T1 to 6, T2 to this 5 in f of q. And so these are the two rings that I have, R and f of q. And somehow I want to prove that f of q, which this is kind of a picture of that ring, is R, which is this ring, mod an ideal. Okay? So how do we do something like this? So this is something that I hope I've drilled in your minds enough in this class, in the previous class, that whenever you have an equality like this, you should know how you prove something like this. This looks like a first isomorphism theorem, and that's what we're going to do. Okay? And so what's the proof? Well, what we need is to use the first isomorphism theorem. How do we do it? Well, what we want is, so what does that theorem say again? It says that the image is equal, so if you have phi of R from R to S, then the image of phi is isomorphic to R mod the kernel. And so we know what we need to do. We just need to build the isomorphism such that the image is this thing, R is R, and the kernel is this thing. Making it happen is a different thing, but at least we know what we're supposed to do, right? So we need to go from R to, we want the image to be this, so let's try to make it happen. Okay. So let me just say we need something like this, such that the image of phi should be f of q. In other words, that this should be surjective. And the kernel of phi should be I sub L. That's what we need. Okay. So how do we do it? Well, what I need to do is I need to take anything in here, right here, our ring R lives here, and I need to send it to something in here. Our ring Q lives here. Okay? So for example, where should I send my variable x1? Well, the thing is that actually I have a map from here to here. And that's the map that probably I should be using. So how does this map work? Do you remember? We said that the first variable, E1, goes into the first generator, A1. So we have that phi of E1 equals A1, phi of E2 equals A2, phi of E3 equals A3. So that's almost what we want, because that's something that allows us to go from this picture to this picture, except that these guys are not ring elements. These are generators. Okay? But if I ask you to map a ring element, I mean, E1, E2, and E3 correspond to, because I use the letters X, Y, and Z, let me switch to using them here. Okay? Or maybe let me switch to that here. So where should I send x1? Well, I have E1 who gets sent to 3, 0. So I should probably send x1 to whatever monomial this thing has. Phi of x1 should be the monomial for this point, which is t to the 3, 0. And phi of x2 should be t of 1, 1, and phi of x3 should be t of 0, t to the 0, 2. Seems like the natural thing to do here. So we define it by, this is a polynomial ring in invariables, and it's enough to just say what I'm doing to each variable, right? And I'm sending the ith variable here to some monomial here, and the natural choice for a monomial is t to the ai. Okay? But this is question mark because we haven't proved these two properties. Okay? So for example, why is this surjective? Well, because I said that as a ring, my semigroup ring f of q is generated by t to the a1, t to the a2, t to the a3. Right? And so if I manage to map something to t to the a1, something to t to the a2, something to t to the a3, that means that the 3 generators are in my image. And if the 3 generators are in, then everything is in. So let me say this. So t to the a1 up to t to the an generate f of q, and they are in the image. So everything must be in the image. So that's why this is surjective. Now, I need to prove that the kernel of phi is equal to I sub L. And this, again, as usual, we do it in 2 steps. First one inclusion, then the other one. So let's take something in here. Okay. Let's take one of the generators of I sub L. And let's prove that it's in the kernel. Let's prove that phi of it is 0. Okay. Well, the thing is that if you think about how that goes in this picture, you have to remember that as I mapped from here to here, I thought of my lattice as this stuff, right? So remember that I told you basically the lattice consists of the things that map to the origin. So because x to the u minus x to the v is in I sub L, that means that u minus v is in L. But L is the kernel of this map, which means that phi of u minus v is equal to 0. But this is a homomorphism, right? So I can say that phi of u is equal to phi of v. So what does this mean? What this means is that I have 2 points u and v which live in Z3 in this case, or Zn in general. Okay? Here's u, here's v. And the condition that they satisfy is that when I map them down, they map into the same point over here. Okay? Phi of u and phi of v are the same guy. But that means that up here, u and v are different monomials, but the way that I define this map capital phi is by exactly saying what does little phi do. So if u and v get mapped to the same guy over here, then the monomials x to the u and x to the v get mapped to the same monomial over here. So in other words, phi of x to the u is equal to phi of x to the v. Or, in other words, phi of x to the u minus x to the v is equal to 0. Which is what I wanted to show, right? Because I wanted to show that this guy was in the kernel of phi. Okay. So that direction is okay. And actually, the other direction is not too complicated, but I'll just ask you to see the book here. I think this is the interesting direction that kind of explains why it is that this is the case. Okay. Any questions about this? Right, so as a lattice, Z3 has 3 generators, E1, E2, E3. Now I'm taking that lattice and making it into a ring, a polynomial ring. And the way that I do that is that I associate to the generators E1, E2, and E3, which are here, the variables x1, x2, and x3. And then, for example, this guy is E2 plus E3. So I associate to it the monomial x1 to the 0, x2 to the 1, x3 to the 1. So it's a correspondence between points in my lattice and monomials in my ring. Okay. And so basically, I mean, actually when I was preparing class, I was deciding whether to use the letter phi or not, when I had already used it here, because I thought I might confuse you. But actually, maybe it's a good thing for you to think that actually these are essentially the same map. They're just kind of 2 different languages. So phi, little phi, Do you know, by the way, this is lowercase phi and this is uppercase phi? Took me a long time to figure out how these letters go, but anyway, so lowercase phi acts on the lattices. Lowercase phi says take a point in this lattice and send it to this lattice according to this linear map. The map that sends the first generator here, the second generator here, third generator here. So that's what little phi does, is it takes a point here and it sends it to a point here. And big phi does the same thing, except that it gets fancier and calls things polynomials, but it does exactly the same thing. Yeah? Big phi takes a monomial here, but a monomial is just a point, and sends it to a monomial here, but a monomial is just a point. So these maps are really the same, except that here we're calling things points and here we're calling things polynomials. Okay? And that's why this theorem is not too surprising and really yeah, I mean, that's basically why this theorem is true. Okay. So I want to just make another quick definition / theorem. And this is the definition of affine semigroups. Okay. Now, I want you to remember that last time I gave 2 examples. So this was my first example. And the other example was when I used Z2. And then my picture was very boring. My picture was just a picture of 2 points. Okay. And basically, whenever the picture looks like this, when it's really kind of honestly living in Zn, I want to call it an affine semigroup. And when it's one of those weird guys that has things like Z mod n in it, then I don't want to call it affine. So affine is basically going to mean that it lives in Z to the n. Okay? But the theorem says this theorem, the following are equivalent. So first, the semigroup Q is affine. And that means that it is isomorphic to a semigroup in Z to the D. Okay. So basically, if it lives in the lattice Zn, then we call it affine. Second statement is that if we look at the group generated by Q, now, what do I mean by the group generated by Q? Q is a semigroup, right? So you're only allowed to add things in Q. But Q lives in an abelian group. And in the abelian group, you are allowed to take negatives. Okay? So Q lives up here, but really it lives inside A, which is over here, right? Here's A. And inside A, you know how to take negatives. And so the group that Q generates is basically what you get when you allow yourself to take negatives. Maybe I'll write it like this. It's basically the group that you get when you allow yourself to subtract elements of Q. Is isomorphic to Z to the D. In other words, what I'm saying here is, for example, Q right now doesn't look like Z squared. But I'm claiming that because it lives in this picture, if you now take the the group generated by Q, in other words, if you take this and now you allow yourself to subtract things in Q also, then actually you're going to fill all these gaps that you found and you're going to get all of Z2. So for example, this guy, I cannot obtain it as a sum as a positive combination of these guys. But if you allow me to subtract, then I can, right? Because I can get to this guy and then subtract and subtract. And you can see that if you allow yourself to subtract this vector, then because we've already filled up all of this stuff, then you can kind of sweep back and fill the whole plane. So that's what this is saying. So in this example, D and E are equal, but it might be that they're different. Because, for example, the picture might be in Z squared, but maybe Q is along a line only. So that's why I switched from D to E. Okay. So these are properties of the semigroup. Now, you can also say this in terms of the semigroup ring. So you can already tell from the semigroup ring whether the semigroup is affine or not. The Q is affine if and only if f of Q is an integral domain. And you can also tell from the ideal. Q is affine if and only if this ideal is prime. So as a consequence for free, because Q looks like this, we get that this specific ideal is a prime ideal, and we get that this ring right here is an integral domain. And if you started with something that was not affine, then those two statements would not be true. Okay? So this is the statement of that theorem. Now, the point, what I want you to get out of this theorem is that this is the nicest family. Right? This is the nicest family. If Q is affine, then all of these nice properties hold. And if Q is not affine, then there are things you have to worry about. Actually, proving this is very easy. For example, here, from here to here, all you have to know is that every subgroup of Z to the D is of the form Z to the E. So this equivalence is very easy. This equivalence is also very easy from here, because remember that your prime if and only if modding out by U gives an integral domain. So this equivalence is also very easy. And then the other equivalent, so these two are easily seen to be equivalent. These two are easily seen to be equivalent. And for these groups, it's not too hard. And I think I don't want to do it because I don't have so much time. But you can see it in the notes, and it's really fairly easy. So proof, see notes. You can see the notes or the book of Miller and Sternfels. I guess I should also say that this talk today, one of the authors is Miller. So Miller is also a student of Sternfels. So it's all very relevant to this. Anyway, so let me just tell you where we're headed next, and then I'll give you a summary of primary decompositions. Where we're headed next is that we have this general setup of lattice ideals, and we have this kind of sub-setup where things behave more nicely. And this is nicer because we have a picture in Z to the n that we can play with. And so what we're going to do next is focus on this setting and translate between properties of the affine semigroup and properties of the ideals and properties of the pictures. Okay. And this is very much the philosophy that Laura is going to talk about today also. So do you have any questions about this before I tell you about primary decompositions? Okay. So let's talk about primary decompositions, and I think that actually what happened is that I talked a little bit about this not in this class but in the previous class, and that's why I feel like I've talked to some of you guys about it, but not in too much detail. So let me just make some definitions. Okay. Now this is very general. This is about rings and ideals. So let's say you have some ring A, and you have some ideal of A, and then we're going to say that this thing is primary if whenever xy is in Q, that means that either x is in Q or y. So far it looks like prime ideals, right? Except that there's an n here. So that's what it means to be primary. Okay, the definition is fairly simple, and it should remind you of prime ideals, right? So, in fact, let me compare it with prime. So a prime ideal is something where if xy is in Q, then either x is in Q or y is in Q. Right? Now, what was the point of prime ideals? The point of prime ideals is that they were supposed to be like primes. And what this is saying in that language, if we talk about, if we say over the integers, then if we look at the ideal generated by a prime, this is a prime ideal. And why is that? Because Q consists of the multiples of P. And so what we're saying is that if xy is a multiple of P, then either x is a multiple of P or y is a multiple of P. That's what it means to be prime, and that's kind of one of the basic things in number theory. Okay? Now, let's look, for example, at something that's not prime, like 4. The ideal generated by 4. Is that a prime ideal? So the question is, if xy is a multiple of 4, does x or y have to be a multiple of 4? And the answer is no, right? Because they could be 2 and 2. Okay? So this is not prime, but it is primary, right? Because if you're a multiple of 4, then either x is a multiple of 4, or if x is not a multiple of 4, then y has to be at least even. And if y is even, then some power of it is a multiple of 4. So I kind of said that. If you write it down, you'll see that it makes sense. And the same argument, the exact same argument, works for p to the alpha. So if, let's call it m. Okay. P prime and m a natural number, then this is no longer going to be prime unless m is equal to 1. but it is primary. Okay. And this is basically saying if you're a multiple of p to the m, if xy is a multiple of p to the m, then the p's have to come from somewhere. And if you allow me to raise to any power, then I can make myself a multiple of p to the m. Okay, so this is fairly easy to show. And so when you think about a primary ideal, what you're supposed to think about is they're like these guys. Okay? So prime ideals are like primes. Primary ideals are like powers of primes. Now, there is, for every primary ideal, there is a clear way of getting, sorry, for every power of a prime, there is a corresponding prime. And this is true at the level of ideals. For every primary ideal, there is a corresponding prime ideal. So let me show you how that goes. If Q is primary, then I can define something. I like the name of this, rad of Q. This is the radical of Q. And by definition, this consists of the elements are in the ring such that some power of them is in Q. So imagine that we do that for the multiples of p to the m. You want the numbers such that some power of them is a multiple of p to the m. And so what we get is all the multiples of p. If you're a multiple of p, then your mth power is a multiple of p to the m. And if you're not a multiple of p, then no matter how many times I try to raise you to some power, you're not going to be a multiple of p to the m. So what I'm saying here is that the radical of p to the m is p. And it works in general that if Q is primary, then its radical is prime. Okay. And Q is called p primary because it's associated to p. Okay. Now, one of the favorite reasons that we consider things like this is because we like to factor integers, right? So we have prime factorization. Every natural number n is a product of primary numbers, where by primary we mean p to the m for some n. And it's actually uniquely so. And we can say this, for example, for 180, that has a prime factorization, which is, what is it? Let's see. 180 is a multiple of 2. It's a multiple of 4. When I divide by 4, I get 45, which is 9 times 5. Okay? And I can say this in ideal notation. The multiples of 180 are the multiples of 4, which are also multiples of 9, which are also multiples of 5. And what I'm writing here is what's called a primary decomposition of an ideal. A primary decomposition of an ideal is a way to write it as an intersection of primary ideals. So something like I equals Q1, intersect etc., intersect QR, where these guys are primary. Okay? So when you think about a primary decomposition, what you should be thinking is that it's like prime factorization, except that you are in any ring, not at the integers. Okay? And then basically what you want to do is start doing number theory, except that you no longer have numbers, and you want to see if things are true. For example, does every ideal have a primary decomposition? Maybe. Not always. Is that primary decomposition unique? Maybe, not always. Okay? It depends how good or how bad the ring is. And so the whole story of primary decompositions is trying to generalize prime factorization to any ring.